Welcome back to another deep dive. I'm
Yeah.
really excited for this one because today our mission is to unpack something that's, well, it's highly provocative,
Yeah, that's definitely the right word for it.
right? And we're tailoring this specifically for you, the learner. Because usually, when we talk about perception, there's this underlying assumption of instant reality.
Oh, absolutely.
Like you turn on a TV or you just open your eyes in the morning and the light hits your retina. Your brain just kind of points at the world and says, yeah, there it is. That's what's happening right now.
It feels incredibly immediate. I mean, our everyday experience basically trains us to view perception as this binary state, right?
Yeah.
An event is either happening right there in front of you in real time or it isn't.
Yeah, we deeply want to believe our eyes are giving us this live, unfiltered broadcast of the universe.
But, when you step into the world of theoretical physics, specifically the realm of relativity, suddenly you realize that live broadcast is actually on a severe tape delay. Like when you look out into a room or across a field, you are not looking at a single present moment. You're looking at a visual landscape that is effectively a collage of the past.
It is the absolute definition of historical muddy waters. And diving into those waters is exactly what we're doing today.
Definitely.
So we're looking at a set of translated Japanese notes from this independent researcher. The author goes by the handle Zynod 2023 online.
Right, and it's a mix of theoretical physics, philosophical musings, and literally 3D modeling.
Yeah, and the specific post we're focusing on is a draft titled Einstein Slacking 135.
Which, the title alone gives you a sense of the tone here.
Oh, they are not pulling any punches at all.
Yeah.
The core premise is massive. The author is arguing that the mainstream physics community has been fundamentally misunderstanding a central pillar of relativity for, 100 years.
Yeah, and they aren't just doing math on a dusty chalkboard to prove it. They're actually rendering the universe using Blender, the 3D animation software, to build these visual Minkowski spacetime diagrams and show us exactly where we went wrong.
So the hook here is, what if objects moving near the speed of light don't actually shrink? What if the famous Lorentz contraction is just an optical illusion caused by the speed limit of information?
Right. It forces us to ask this really uncomfortable question about how we do science. Like, are we constantly confusing what we see through a telescope or even our own eyes with what is actually physically existing in that space?
It's a huge question. But to understand this grand claim, we first have to examine the author's primary critique of modern physicists, which is that they've essentially lost touch with physical reality.
Yeah, by falling too deeply in love with the equations themselves, the author actually uses the term math-obsessed theoretical physicists.
Okay, let's unpack this.
Yeah.
Because, how do you lose touch with physical reality when your entire profession is literally the study of physical reality?
Well, to see where this stems from, we have to look back at the history of physics, all the way back to Newton's laws of universal gravitation.
Okay.
When Newton formulated his math, physicists treated the universe as if information traveled instantaneously.
Right.
Like, Newton calculated gravity as if the sun and the earth communicated their mass and distance to each other with zero delay.
Like a magical invisible string connecting the planets that just tugs them simultaneously.
Exactly. That is the perfect way to visualize the classical mindset. It was treated as an instant action across the vacuum of space.
But then, obviously, we enter a post-Maxwell world.
Right. James Clerk Maxwell gives us the foundation for electromagnetism in the 19th century and proves that electromagnetic fields, and therefore light itself, have a strict, unbreakable speed limit.
Right. Information cannot travel faster than the speed of light in a vacuum.
Exactly. So suddenly, that invisible string has a transmission delay.
Which introduces a massive problem for anyone trying to measure the universe. And the author uses this brilliant analogy to make the mathematical disconnect relatable.
The CEO analogy.
Yeah, the CEO analogy. Think of a CEO. A CEO sits in their corner office, high up in a skyscraper, and they often view their sprawling company as a single instantaneous point.
Right. They pull up a spreadsheet and think, this is the state of my company right now.
Exactly. But a real multinational corporation is spread across thousands of miles. If that CEO sends a command to a plant on the other side of the planet, it takes time for that directive to travel.
Right.
And when a production report comes back from that factory, the data on the page is already old news by the time it hits the CEO's desk.
So true.
So the author points out that physicists have effectively forgotten they have a body size and a delay in receiving their cosmic reports. They're treating vast spatial measurements as if everything happens instantaneously, right there in the CEO's office.
What's fascinating here is how the author sets up a 3D Cartesian coordinate system, so your basic X, Y, and Z axes, to mathematically correct this CEO problem.
Right, to fix the illusion of instant information.
Yeah. Instead of assuming an omniscient, godlike view where we see everything at once, the author places a camera eye at a specific coordinate on the grid. In their model, this camera is placed along the y-axis at y equals -10.
So you take a step back from the center of the action, you're observing from a distance.
Exactly. This camera acts as the observer's screen, the CEO's desk, essentially. And because light takes time to travel, we have to calculate the distance from any event back to that camera.
Okay.
If the camera looks straight ahead at the exact center of the universe coordinate 0, 0, 0, 0, it takes 10 units of time for the light from that center point to reach the lens.
Meaning the camera is never seeing the center as it is at this very millisecond. It's seeing a 10-second-old historical event.
Right. And the math gets even more complicated when you look away from the center.
Oh, because of the angles.
Exactly. If the camera looks off to the side, let's say at x equals -10, the light isn't traveling in a straight line toward the observer anymore. It has to travel along a hypotenuse.
So Pythagorean theorem kicks in.
Yeah, that distance is longer, meaning it takes about 14 seconds for that light to arrive.
Wow. So what does this all mean for you listening to this right now? It means the universe you see, the room you're sitting in, the scenery outside your window, none of it is a single snapshot of the present.
Not at all.
It is a mosaic of different pasts. The center of your vision might be a fraction of a nanosecond old, while the edges of your vision are slightly older because the light had to travel further to hit your pupil.
It completely shatters the illusion of a simultaneous reality. We are perpetually trapped inside a bubble of delayed information.
But, okay, if our eyes are just feeding us a collage of old news, that creates a massive engineering nightmare. I mean, how do you actually measure the speed or size of something moving through that mosaic?
You can't just snap a photo.
No, you can't. And the author actually uses a fantastic real-world engineering analogy to solve this measurement problem.
Right, moving from the abstraction of theoretical space to the concrete reality of aerospace engineering.
We're talking about the pitot tube.
Yes.
For anyone who might not be an aviation nerd, a pitot tube is this little L-shaped metal instrument that sticks out of the nose or the wing of an airplane. Its entire job is to measure the airspeed of the aircraft.
And it does this by measuring two distinct things, right?
Right. It measures the total pressure at the front opening, where the air is slamming directly into the tube, and the static pressure at a small side hole, which is totally unaffected by the direct forward airflow.
By comparing those two pressure readings, the plane's computer calculates how fast it's moving through the air mass.
Exactly.
And the author brings this mechanical concept back to our delayed coordinate system. So imagine that airplane is massive, stretched out infinitely along our x-axis.
Okay, I have the picture in my head. A giant plane.
The front sensor of the pitot tube is placed at x equals 10, and the side sensor is placed further back at x equals 0.
Two sensors spread far apart. Got it.
The physical data from these two sensors has to travel through wires to reach the central computer, which in the author's model is located all the way back at x equals -10.
Back at the CEO's desk.
Right. So let's calculate the travel time for that data. The information from the front sensor, way out at x equals 10, has to travel 20 units of distance to reach the computer at -10.
Okay.
That means it takes 20 seconds for the front pressure reading to arrive. But the information from the side sensor, sitting at x equals 0, only has to travel 10 units of distance. It arrives in just 10 seconds.
Wait, let me push back on this. If the data hits the dashboard at completely different times, the pilot's speed reading is going to be total garbage.
Right.
Like if the computer compares a 20-second-old pressure reading from the nose with a 10-second-old reading from the side, the plane could have gone into a dive in that 10-second gap.
Yeah.
You can't calculate speed with mismatched timestamps.
And that is the exact trap the author is highlighting.
Oh, I see.
If you blindly take the data the moment it hits your desk and crunch the numbers, you're making a fundamental error about the physical state of the airplane. You're treating delayed perception as immediate reality.
So how do you fix it?
This brings us to the author's solution. An abstract capacitor.
An abstract capacitor. Okay, in electronics, a physical capacitor stores electrical energy and releases it when needed.
Right, but here the author uses it as a conceptual device to store information. The central computer receives the side sensor's data after 10 seconds. But instead of throwing it into the speed equation immediately...
It holds it.
Exactly. This abstract capacitor holds on to that 10-second-old data for an additional 10 seconds.
It artificially pauses the faster information.
It waits in a buffer until the much slower 20-second-old data from the front sensor finally completes its journey down the wire. By intentionally delaying the faster signal, the abstract capacitor synchronizes the historical timestamps.
Oh, wow.
So the computer is finally comparing the front pressure from time 0 with the side pressure from time 0.
Even though the computer's physically doing the math at time 20. The CEO has to consciously look at the dates stamped on the factory reports, sort them, and reconstruct the past to understand the true present. You cannot just read whatever lands in your inbox first.
And this specific concept of synchronizing delayed timestamps is the exact key the author uses to dismantle the traditional teaching of Einstein and Lorentz's relativity.
Because if we take this aviation problem and scale it up to the speed of light, we hit the most famous thought experiment in physics. This is where the author really takes aim at the history books.
Yeah, we have to talk about Hendrik Antoon Lorentz.
Why?
He was a brilliant pioneer, and the author's notes actually suggest Lorentz was one step away from getting the architecture of the universe entirely right.
Like even before Einstein published special relativity.
Exactly.
Anyone who has taken, a college physics class has heard of the Lorentz contraction. The traditional textbook teaching states that if an object, say, a really fast-moving train, is moving near the speed of light, it physically shrinks in the direction of its motion.
Right, the actual space it occupies compresses. The train becomes shorter.
But the author, Zamanad 2023, argues this physical shrinking is completely false. The train's metal chassis is not compressing. The space around it is not bending.
No. Instead, what Lorentz discovered with his famous map wasn't a physical contraction of the universe, but a mathematical necessity for a Lorentz correction.
A correction, not a contraction.
Right.
So what does this all mean? Let's visualize the author's train scenario to see how this actually works.
Yeah.
Imagine a massive train. Let's say it has a length of 20 units, blasting through space.
Okay.
Because the train is so long, the light bouncing off the front engine, the middle dining car, and the rear caboose all have to travel different distances to reach our observer's camera eye.
It's the pitot tube problem all over again.
Exactly.
The light from the front of the moving train might take 20 seconds to reach you, the middle takes 10 seconds, and the back takes 5 seconds.
So if you just snap a photograph as the train zooms by, the light hitting your camera lens right at that instant is a completely jumbled mix. You're capturing the front of the train from a long time ago, and the back of the train from a slightly less long time ago.
And because the train was rapidly moving forward during those travel times, the front of the train in your photo appears much closer to the back than it actually is in physical reality.
It looks squished.
The photograph makes it look squished. But the author stresses that the spatial and temporal axes of the physical universe are not deforming at all.
Space isn't bending.
Space isn't bending to accommodate the speed. Time isn't literally slowing down. The contraction is just a simple trick of near-action information delay.
But wait, if it's an illusion, why do we use Lorentz's complex math at all?
Because you need a way to build that abstract capacitor into your observations. To understand this, we have to look at Minkowski space-time diagrams. Think of a Minkowski diagram as a map that treats time as a physical direction. Instead of just a 3D box, you swap out one spatial dimension for time, creating a sort of flipbook of the universe.
So you can trace exactly where an object is and exactly when the light left it.
Exactly. When you step inside that diagram, when you become the person inside actually getting hit by the delayed light rays, you realize you just need to mathematically correct for the delay of the light arriving from the train's extremities.
So the Lorentz equations are the abstract capacitor.
Yes. You use the math not to describe how the universe is magically shrinking, but to correct your delayed visual data back to reality.
You use the equations to sync up the timestamps of the light hitting your eye, so you can figure out how long the train actually is.
And the author claims mainstream physics has been failing to recognize this subtle distinction for a century.
Wow. They've been treating the distorted photograph as if it is the physical object.
Exactly.
That's a staggering critique. And it makes intuitive sense when you frame it entirely around the speed of light delay.
Yeah.
But, it leaves a massive question hanging in the air.
Which is?
If the train isn't actually squishing like an accordion, then what does it actually look like when it zooms by at near light speed?
Right. If the pancake squish is the wrong optical illusion, what is the correct one?
Yeah. And this is where the author's work with 3D modeling comes in, and it provides a visual answer.
And they back it up with actual software.
Right. They don't just leave us with abstract equations.
Yeah.
To understand the 3D models, we have to introduce the Penrose-Terrell rotation.
Ah, this is such a cool concept.
Here's where it gets really interesting. This rotation concept was independently theorized back in 1959 by physicists Roger Penrose and James Terrell.
And it somehow gets totally overshadowed by the shrinking train idea.
Totally. So imagine a perfect solid cube moving past you at a significant fraction of the speed of light. The old contraction theory tells you that you just see a squished front face, like a flat rectangle zipping by.
But Penrose, Terrell, and our blog author argue that is entirely wrong.
Because of the delay. The light from the back of the cube takes longer to reach your eye than the light from the front face.
Right. As the cube moves rapidly across your field of vision, the light from the trailing side of the cube, the side that should theoretically be hidden from your view, actually has time to catch up and hit your retina.
It's mind-bending. You actually see the side of the cube at the exact same moment you see the front of the cube.
Yeah.
The delayed light creates a visual distortion where the object doesn't look compressed. It looks like it is physically rotated toward you.
It is a pure optical rotation. And the author validates this using actual 3D Blender screenshots provided in the source material.
Right, they built a digital environment.
Yeah, they call it the Minkowski Stable V7.
Which is a fantastic name, by the way. Minkowski Stable V7 implies they spent hours trying to get the software to break or prove them wrong before arriving at version 7.
Oh, for sure. And looking at the specific parameters from the author's UI screenshots, we can see the exact math they fed into the engine. They set the speed of a target object to beta equals 0.3000.
So 30% the speed of light. Fast enough for relativistic effects to show up.
Exactly, and the screenshots show these visual layers they toggled on, labeled as light cones, time-like rays, and space-like rays.
So what do those actually look like in the software?
Well, imagine dropping a pebble into a still pond. The ripples spread out in a perfect circle over time. A light cone is essentially the 3D version of those ripples. It maps exactly where and when the light from that moving cube can physically reach the camera's lens.
Okay.
The space-like and time-like rays trace the exact geometric paths of that delayed information.
So in the dark void of the 3D software, these rays look like brightly colored intersecting tubes. They're literally mapping the travel time of the light from every single corner of the cube back to the camera.
Right, and by plotting the intersections of these rays in 3D space, taking into account the rigid speed limit of light from different points on the object, the software natively renders the Penrose-Terrell rotation.
That is so cool. The 3D engine isn't programmed with a specific make the cube rotate animation. It is simply programmed to enforce the speed of light. The rotation is just a natural mathematical byproduct of the delay.
The author proves that this optical rotation is just a visual effect born from the speed of light, not physical space collapsing in on itself.
They're literally using commercial computer graphics to audit a century of theoretical physics. The software acts as an uncompromising universe, and the result isn't a squished cube, it's a rotated one.
It is a profoundly powerful way to bridge the gap between abstract equations and physical reality. It forces us to acknowledge the medium we are looking through.
Which brings us to why this incredibly intense physics deep dive actually matters for you, our listener, in your daily life.
Definitely.
Because the author explicitly references the famous quote, "The map is not the territory."
Such a vital concept. The model we use to understand reality is not reality itself.
Right. The photograph is not the physical train. The CEO's delayed spreadsheet is not the buzzing factory floor. And our eyes, amazing as they are not giving us a live, real-time feed of the universe.
No.
We must be so incredibly careful not to confuse our mathematical models or our naturally delayed visual perceptions with the actual physical reality happening out there in the world.
It serves as a stark warning against arrogance in measurement. Just because you have a clean number on a screen or a vivid visual image in your brain does not mean you understand the true current state of the system.
Yeah, you have to account for the delay.
You have to actively account for the medium and the speed of information itself.
It really makes you second-guess the reliability of your own vision.
It does. And, this raises an important question, and it's a final thought I want to leave you with to mull over.
Let's hear it.
If we connect this to the bigger picture, If everything we see, the stars, the person sitting across from us, the screen in front of our faces, is just a collage of light that departed at different times in the past.
Because even the light from your phone takes a fraction of a nanosecond to reach you.
Right. If everything we interact with is a delayed historical record, does the present moment even exist as a shared reality? Or is now just an abstract capacitor we've built in our own minds to make sense of a delayed universe?
Oh, wow. An abstract capacitor in our own minds. We are all just walking around desperately trying to sync up our historical timestamps so we don't go crazy.
Exactly.
That is quite the thought to mull over the next time you look up at the stars or, just across the living room. Thank you for joining us on this one. Until next time, keep diving deep.